Sometimes when a solvent is cleaned, reclaimed, or even replaced, the facility operator will keep back a few drums of the old solvent. Ever wonder why? My name is Simon Weiland. I'm a technical applications engineer with Optimized Gas Treating, and together we'll walk through an actual case study and find out. The case is a conventional tail gas unit, or TGTU, in a refinery that was using 34 weight percent MDEA to treat tail gas from a sulfur recovery unit containing 1.7% H2S and 3.4% CO2. TGTUs are typically run on a separate solvent circuit. However, this one was being run as part of the refinery's overall MDEA system. Although solvent analysis showed several different heat-stable salts being present, with a total accumulation of 0.8115 weight percent, the unit was producing a vent gas containing 3 to 4 parts per million H2S. However, the heat-stable salt level was getting high, and heat-stable salts can be corrosive at high levels, and so the decision was made to reclaim the solvent. At the same time, the unit was looking to increase capacity by switching from trays to packing. After reclaiming and the internal switch out, the vent gas jumped to 38 parts per million H2S, an increase of around 10 times. Replacement of trays by packing was blamed by a consultant. The recommended solution was to remove the packing and reinstall the trays, because trays would increase the residence time. Unfortunately, when the unit was brought back up after being out of service for several days to reinstall the trays, the treating performance remained completely unchanged, still being in the high 30 parts per million range. This is where OGT came in. A digital twin of the complete TGTU was set up in ProTreat, OGT's mass transfer rate-based amine treating simulator. It was used to model the complete plant as it was before the shutdown, including all the heat-stable salts, the regenerator with a known tray count, and reboiler duty. The predicted treat was 3.94 parts per million H2S, compared with the originally measured level of 3 to 4 parts per million. When the unit was resimulated without heat-stable salts, the H2S leak was predicted to be 32.6 parts per million. If a model that did not account for heat-stable salts at all had been used, the predicted treat would have always been around 35 parts per million, more than 10 times higher than the actual performance. The not-so-obvious lesson, then, is that, in a TGTU, a clean solvent will not treat to as low a residual H2S level as a solvent contaminated with heat-stable salts will. That's the reason why refiners often store a few drums of contaminated solvent before undertaking solvent reclaiming or replacement. This graph shows the effect of various levels of heat-stable salt removal, or degrees of reclaiming, on lean solution quality and H2S treat. Notice from the table that CO2 slip is hardly affected by reclaiming, but reclaiming has a tremendous effect on the unit's H2S leak. Notice also the lean loadings of H2S. When the solvent contains its full complement of heat-stable salts, lean loadings are reduced by a factor of nearly 40 for H2S compared with a clean solvent. The second lesson is, the processing effects of heat-stable salts is really felt in the regenerator, where much lower lean loadings can be achieved when the solvent contains heat-stable salts. Perhaps this should not be so surprising. After all, it's well known that the addition of a small amount of mineral acid can give superior tail gas treating. Intentionally acidified amines and amines containing heat-stable salts all promote solvent regeneration by the same mechanism. They shift the equilibrium of reactions that occur between acid gases and the amines. For example, when H2S is present in an amine solution, such as MDEA, very little of it exists as dissolved H2S molecules, because when H2S chemically dissociates in the solution, the hydrogen ion it produces is neutralized by the amine. When part of the amine is neutralized by a small amount of mineral acid purposefully or by heat-stable salts as contaminants, the concentration of the protonated form of the amine is higher than it normally would be. This tends to push the reaction equilibrium to the left. Displacement to the left favors decomposition and the formation of free H2S. This is the mechanism that takes place in a regenerator, and therefore stripping is favored. At high loadings, the impact is minimal because the protonated amine concentration is already very high. But in the reboiler, the H2S loading should be very small, so even a small amount of additional protonation is very significant. In fact, the additional protonation can be factors of 10 higher than what would normally be found in a well-regenerated clean MDEA solution. Of course, the higher H2S back pressure caused by protonation affects absorption negatively. However, it turns out that its beneficial effect on reducing the lean loading outweighs its negative effect on back pressures in the absorber. The result can be easily a factor of 10 to 20 times lower H2S leak when heat stable salts are present in small amounts. Of course, caution is needed not to let heat stable salts build up too high because they are corrosive. But caution is also needed not to reclaim too aggressively or treat may be lost. The main lesson here is that reclaiming decisions should start with a good set of simulations generated using the ProTreat process simulator with its high accuracy and reliability. The simulator must also be able to model the actual system under study, especially the detailed solution chemistry and the mass transfer behavior of the real column internals being used. As in this case, accurate regenerator modeling can be just as important as simulating the absorber, and ProTreat does both extremely well. OGT's two main products are ProTreat and SulfurPro. ProTreat is a mass transfer rate-based process simulator, and it's unique in its ability to accurately model acid gas removal systems, as well as many other gas treating applications. SulfurPro is our rate-based sulfur recovery process simulator. It has state-of-the-art capabilities not found in any other software for accurately modeling the modified Claus sulfur recovery process. Fully flexible flow sheets allow simulations of nearly any SRU configuration fully integrated into upstream and downstream gas processing operations. Together, these tools provide our customers with expertise in optimizing, troubleshooting, and designing units to minimize CapEx and OpEx in order to maximize profitability. We have a lot of great resources on our website at www.ogtrt.com, including numerous publications on gas treating and sulfur recovery, as well as tips and tricks to get the most out of the software. In addition to our software products, OGT offers consulting services. To learn more, visit our website where you can see actual additional case studies from our work. At OGT, we're working for a more sustainable environment through the use of simulation tools to optimize and troubleshoot your plants, while at the same time lowering your costs and maximizing profits. We can be reached by phone or internet as shown here. Thank you for watching, and I hope that you have learned how ProTreat's mass transfer rate-based simulator not only identified and solved the problem, but provided sustainable operating curves, giving the plant operators more confidence and a much more robust plant.